So today at Not at Lunch, we have Nancy Scherich who will tell us about the braid groups and their representations.
Thank you for the introduction and thank you for inviting me to speak. I think I sort of invited myself to speak, but yeah, so I'd originally intended to tell you about this construction that Dror and I have been working on, but then as I was writing my talk, I had so much preliminary stuff that I wanted to talk about that I don't think I'm actually going to get to the new construction at all. So hopefully this will just be kind of a survey, in-depth survey about braid groups and their representations and kind of how to think about them. And then if you'd like to learn more about the stuff that Dror and I have been doing, I'd be happy to talk to you about that. Okay, so what are the braid groups? So Leonard started us off last week, so this is a nice kind of jumping off point from his talk today. But just a reminder, the braid group, you have to tell me what number of strands you're working it with. So that parameter is usually denoted n, and so you say Bn to be the braid group on n strands. And here's the group presentation for this group. You have n minus 1 generators, so whatever your strand, the number of strands you have, you always have one less than that as the number of generators. And you have these two relations. But probably the best way to think about this group is not so much from this presentation, but sort of remembering the pictures that go along with these relations and generators. So let's talk about how you can visualize the braid group. So each generator, sigma I, is a crossing in the ith position. So here you have the strand that starts in the ith position, and then the strand in the ith plus 1 position, and sigma I is going to be the crossing or the braid that just has a positive twist where I crosses up and over the strand in the ith plus 1 position, and then all of the other strands do nothing. And so then every braid can be built by just stacking little generators or little pictures of this type. Okay, so the first relation is the far commutativity relation. And basically what this says is that if you can separate your crossings, sort of if they're far enough apart, then they commute. So if you're thinking about braids, we're really thinking about these diagrams as like physical pieces of string in space. So if your strings were nailed down to the floor and then nailed to the ceiling, the strings are allowed to kind of blow in the wind. And so that might change their configuration and how the crossings look, but we want to consider them the same braid anyway. So if your crossings are far apart, then they commute. And so algebraically, we just say that those generators would commute as long as I and j are not next to each other. But if your crossings sort of interweave with each other, if you can't separate them, if they're connected, then they satisfy the braid relation instead of commuting. And so this is just the Reidemeister 3 move. And I like to see this as if you take this middle strand here, you can sort of push it through to be on the other side. And this is just a different configuration that those strands could take. And this is the braid relation. So that's the braid group. Hopefully you all have seen it before. But if not, I'm happy to be the first one to tell you about it. Okay, so what are some fun facts about the braid group? So the first thing to notice is that the braid group is infinite. And one easy way that you can see that is if you just take sigma 1, which is like, the first generator, or just the first two strands are twisting, you could just keep twisting and twisting and twisting and twisting forever, and you could create an infinite number of braids that way. And so this group is very infinite. Jumping down here to this last fact, the braid group is torsion-free, meaning it doesn't have any finite order elements. And this is a very useful fact. So each one of your generators has infinite order, because you could just keep twisting and keep twisting. But you're never going to encounter a braid that if you do it multiple times, it sort of counteracts itself. So basically the braid group is very infinite and everything has infinite order. There's no torsion whatsoever. Some other nice facts coming to this third one here is that the braid group has a non-trivial center. And this was really surprising to me when I first learned it, because the generators don't necessarily commute. They commute with, each generator commutes with the generator that's far away, but it doesn't commute with the generator that's next door. So this is not an abelian group, but it does have a cyclic center. So the center is generated by the full twist. And so that full twist, here's a picture of what the full twist looks like. Each strand starts and ends, it sort of makes the full loop around like I kind of like to think about it as like you're wrapping ribbon around a post or something, and you have to go all the way around the post and come back, and every ribbon does the same thing. And that element generates the center, so it commutes with everybody. So kind of a fun little exercise is to convince yourself that this braid actually commutes with everybody. So all you'd have to do is show that it commutes with every generator. So there's kind of a fun way to visualize it, but that might be a fun little thing for you to think about. Can you prove that this element actually commutes with every generator? And another fun fact is that each braid group contains all of the smaller braid groups. So in particular, if you have a braid on n-1 strands, you can think of it as a subgroup of the braid group with n strands by just adding a strand to the end that doesn't interact with any of the crossings. So, you know, if you have 5 strands and you just think about the braids that only use the first 4 strands, if you collect up all of those braids, that's going to be the braid group on 4 strands, and it sits inside the braid group on 5 strands. You could have similarly put the strand that did nothing in the front. So like at the front of the braids or the back of the braids, doesn't really matter. But every braid group contains all of the smaller braid groups and contains it in multiple ways. So that's kind of a good fact to know. Any questions so far? Oh, okay. Shout it out if you do. All right, why should you care about braid groups? I mean, there are tons of reasons to care about braid groups. I mean, I just think they're really pretty and they're fun from that perspective. But braids show up in lots of different scenarios and settings in mathematics, sort of particularly in algebra and topology. The braid groups are sort of smack dab in the middle there. But braids also show up in physics a lot, which is kind of interesting. But the braid groups kind of have their fingers in lots of different areas of math. And so you'll see braids come up from various different perspectives. And so they're kind of well integrated into mathematics. So let's focus a little bit on how the braid group shows up in topology. I mean, I don't know if you guys consider yourselves topologists or algebrists. I think that's always a difficult question. I think I've called myself a topologist, but maybe I'm more of an algebrist. I don't know. But anyway, let's take a look at a few of the settings where braid groups show up very naturally in topology. So where I first learned about the braid groups was from the perspective of knot theory. And this is actually called Alexander's theorem. And Alexander's theorem says that if you have a diagram of a knot, any knot or link, you can always rearrange the crossings and sort of like change up the diagram so that it looks like the closure of a braid. And what the closure of a braid is basically you put all of the crossings into a little braid, and then you're going to connect up the endpoints at the top and the bottom without adding any new crossings. And so anytime you have a knot or a link, you can always force it to be the closure of a braid. So basically braids are sort of encoding all of knots. Like any knot and link is a braid. And any braid, if you take the closure, you're going to get a knot and a link. So braids are super important in knot theory. One scenario that braid groups show up is they're the fundamental group of a configuration space. I'm not super comfortable with this perspective. I don't really think about it a whole lot, but the braid group does show up as a fundamental group of something. And so basically what you do is you look at tuples in the complex plane so that no 2 entries in your tuple are the same. So you just want every entry to be a different number. And then you can act on those tuples by the symmetric group, by permuting the tuples. And so then if you take that space and quotient out the action by the symmetric group, then you get a topological space that's called the configuration space. And the fundamental group of that thing is the is the braid group, excuse me. So the braid group shows up as a fundamental group, and that's pretty interesting. And then something we'll talk about today is about mapping class groups and how the braid groups show up there. And the braid group is the mapping class group of the n-punctured disk. So if you take a disk and then you have like n punctures or n marked points, then the mapping class group is the space of sort of like nice homeomorphisms of the disk back to itself. And it has to be like orientation preserving, and then it's sort of up to homotopy. Like there's a little bit of subtlety here for what the mapping class group is, but basically it's homeomorphisms of the disk to itself. And the way that you can kind of see this, or the way that I like to think about homeomorphisms is sort of like painting your surface. So if you have sort of your surface already nice and painted, you can think about like pushing the paint around. Like, have you ever seen those like YouTube videos of where you put the paint on the surface of the water and then you can drag like a stick through it and it changes the way the paint looks? You guys ever seen that before? Or like where you put paint on a canvas and then spin the canvas and the paint like spreads out. Anyway, that's how I think about mapping class groups. And so how you can see a braid acting on this is you can permute the marked points, permute the punctures, and that's going to change the way the paint looks on the surface. And so you're going to be like moving the paint around, and that's giving you a homeomorphism of your disk. Okay, so these are just 3 examples of where the braid groups show up as like very fundamental pieces in topology, as mapping class groups, fundamental groups, and then this Alexander's theorem, braid sort of encode a lot of knot theory. Okay, so what is a representation of the braid group? So as Leonard talked to us last week, a representation is a homomorphism, a group homomorphism from your braid group or whatever group you're looking at into some general linear group, into some group of matrices. Another way that braid group homomorphisms or that braid representations are thought about is instead of thinking of it as a group, you can think of it as an algebra. So take the complex group algebra of the braid group and then give me an algebra homomorphism into some ring of matrices. That's a very common way to think about representations of the braid group. All right, so we're looking for homomorphisms that turn braids into matrices. That's the name of the game. So why should we care about representations of the braid groups? Why is this an interesting thing to do? And how on earth do you turn braids into matrices? Like, that's a complicated process. How do people come up with these representations? So let's start with why you should care about representations of the braid group. So what are some of the applications of representations of the braid? And with respect to the braid groups, an application that I think is like pretty interesting, or sort of where I first fell in love with braids, has to do with knot invariance and computing knot invariance. So for example, the Alexander polynomial can be computed this way. You give me a knot, and then I'm going to turn it into the closure of a braid. So you can think of the trefoil knot as like some braid with 3 crossings or whatever. Then I'm going to use the Burau representation, which we'll talk to in a minute. Oops. And I'm going to take that braid and turn it into a matrix. So it's going to give me some matrix with polynomial entries. And then you have to do a little bit of work. There's a rescaling and something you have to do. But ultimately, you take the determinant, and what you end up with is the Alexander polynomial. And so these representations are sort of a critical way of turning your braid, turning the braided like diagram information into like more like mathematical information. Like you're turning it into a matrix with polynomial entries. And that's how you're able to make that jump from diagrams to polynomials. It's through that representation. And there are other knot invariants that can be computed in a similar way. So that's a really nice application of why you might care about representations. Another application, which is sort of new and upcoming, is in the field of topological quantum computing. So I think this is really cool. I don't know a whole lot of the details, excuse me, and I'm definitely not a physicist, but here's kind of what the word on the street is. So we've all heard of quantum computing, right? And it's sort of this new way of doing computation. And a topological quantum computer is a way of modeling these types of computations. And so there's sort of this physical system that is like this very thin, like polymer or something, I don't know exactly, but it's this very thin material that's like maybe liquid or something, and it's like frozen. They have to keep it very, very, very cold. And there's these special particles in it that are called anyons. And these particles are very, very sensitive. They're entangled with each other. I think entangled has a very specific meaning in physics. But the idea is that these particles notice their position with respect to the other particles. So if you swap their position, the particles remember that you did that. And so you have these particles, and what you do is you swap them, swap them, swap them, swap them, swap them, and then you want to read off the state of the system after you've done all that swapping. And that is a way of modeling quantum computing. And so if you were to think about what does it mean to swap those points around, well, what you're doing is a braid. So over time, you're braiding those points, right? And then in order to read off the information of a system, you have to do a unitary operation. And so in order to do that, you're going to basically write down your braid as a unitary matrix. And so you need a unitary representation of your braid group. And so picking different unitary representations of your braid group give you different models of this topological quantum computing. So that's super fascinating. And I don't understand any of the physics behind it, but sort of the name of the game for topological quantum computing is you want unitary representations of your braid group. And you also need them to be like local, and there's all these other properties you need. But for example, the Burau representation, which is one we'll talk about in a minute, satisfies all the conditions, and so it can be used to model topological quantum computing. So that's really cool. Question?
Yeah. So is this where the one can apply the use the configuration space? So realizing the braid group as the fundamental group of the configuration space.
No, this is more of the mapping class group perspective. Mm-hmm. Yeah, so we're going to see when we're going to talk about the Burau representation, and we're going to see how the mapping class group perspective is kind of showing up there. But yeah, it's not quite the configuration space. Like you're moving points around, but it's a little different, like because they're planar. You're moving points around in a planar way versus the configuration space. You're in an n-dimensional complex space, and then you're acting on tuples there. So it's that's a much like bigger setting. Any other questions? Okay, so hopefully I've convinced you that representation theory of braid groups is super interesting. There's lots of applications, and like it's worth thinking about, and a lot of people have thought about it. Yeah, so this leads to the next question of how do you find a representation of the braid group? Like, how do you turn braids into matrices? How does one come up with these representations? And turns out there are lots of ways to do it. And part of the reason for that is because the braid groups do show up in so many different ways. Like we have them as a mapping class group, they're a fundamental group. Some examples I've listed here, if you have solutions to a Yang-Baxter equation, that gives you representation of the braid group. What I did a lot of my thesis studying was the Hecke and BMW algebras. And so these are algebras that are much bigger than the braid group algebra, but they induce representations of the braid groups. And so from an algebraic perspective, you can get representations of the braid groups. So there are so many representations of the braid groups, and I think it's because of this reason that we have so many different ways to think about and to study the braid group. And so there's just lots of different ways of constructing these representations. So as I promised before, we're going to think about this mapping class group action and how that gives us the Burau representation. Any questions?
Were you going to say something about thin subgroups?
Oh, I mean, that was just what my thesis was on. So do you want me to think about it?
If you have other things to get to, it's okay. I mean, it's up to you, yeah.
Okay, yeah, maybe what I'll say is like, this isn't necessarily like particular to braid groups, but thinking about representation theory is often a way to come up with special matrix groups. So when you have a representation of your braid group, your image is a matrix group. And oftentimes, because it's coming from a representation, the image is going to be a very special or very nice kind of subgroup. And so part of my thesis was to use it to find thin groups, which are finite index subgroups in lattices. And so, or did I say that right? I haven't thought about this in a while. But there are very specific groups that sort of are spread out in a very thin way. And these are useful in arithmetic group theory, which I don't know much about. But basically, representations have a lot of structure. And so you can oftentimes get lots of like interesting groups and subgroups and stuff from them, just from the manner in which they're constructed.
Cool, thanks.
Yeah. Anything else? Okay, so as promised, let's talk about the Burrell representation. So the Burrell representation is probably the easiest or like smallest or cutest non-trivial representation of the braid group. It's kind of the first one everybody learns. And this is the reduced Burrell representation. There's an unreduced Burrell. They're very similar. Don't get tripped up on that idea. But here it is. In order to give you a representation, I just got to tell you where to send the generators of the braid group. And you would just have to check that these matrices satisfy all of the relations of the braid group. And then voila, here's a representation. Few things to note about this. There's a lot of zeros going on, sort of padded by the identity matrix. And then you have this little 3x3 block that's kind of going chug, 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 chug along the diagonal. And that 3x3 block is sort of encoding the crossings, the little, like, you know, the sigma I has a crossing between I and I plus 1, the strands. And so that 3x3 block is encoding that little crossing along the way. Yeah, it has a parameter. So it has this variable t that shows up in there. And this is the representation that you would use in order to compute the Alexander polynomial. So once you get a matrix like this, it's going to have polynomial entries. It actually has Laurent polynomial entries. So these coefficients have t and t inverses in them. Yeah, okay. So when you see a representation like this, you go, well, fine, great, those look like nice matrices. But how on earth does one come up with these matrices? Like, where did these come from? How do you find these matrices? Where did they come from? And like, it's not so easy to just try to write down some matrices that satisfy the braid relations. Like, that's actually quite hard to do. So I want to just kind of give you a quick little sketch about where the topology comes in and how you can utilize topology to get a representation of your braid group. And we won't go through all the details because there's a lot of algebraic topology, but I just want to kind of give you the flavor of how to use topology to get a representation. All right. So in order to write down a representation, what we need is an action of the braid group on some ZT module. So again, this Z of t here, it's not, this is technically the Laurent polynomials in one variable. I'm just going to call it ZT because it's long. But anyway, we need an action of the braid group on some ZT module. Or another way to say that is you need to view your braids as isomorphisms or endomorphisms of some ZT module. And once we do that, that's how we're going to get, like, that's what gives us a representation, right? So if you think back to your linear algebra days, a linear transformation is the same thing as a matrix. So we're basically we need to define a linear transformation, and that's going to give us the matrix. All right. So as we said before, the braid group is the mapping class group of a disk with n mark points or n punctures. And the sort of way you can think about it is if you're permuting those punctures around, that's going to be changing the way you're painting the surface, and that's describing a homeomorphism of the disk back to itself. Okay, so this is the underlying topological thing about the braid groups that we're going to use. Okay, so we're in search of a ZT module that we can let the braids act on. So right now we have a way of letting braids act on this disk, but we need it to act on some sort of module, like with ZT coefficients. So it turns out the right thing to do is to look at the infinite cyclic cover of your disk. And this is a very standard thing to do from the perspective of algebraic topology. So this might seem kind of like weird if you've never seen it before. But if you're studying algebraic topology, this is something that if you're just following your nose, you would have landed at eventually. Okay, so how do you make this covering space? What do you do? Well, you take your punctures and then you're gonna slice. You're gonna cut a little slice going along to the boundary, right? So you're gonna cut and then you're gonna pull apart that cut and then turn it into little ramps. So everywhere you cut, you turn it into little ramps, and then you just glue those on top of each other. And what you end up with is this like infinite parking garage. So it goes infinite in both directions, where there's ramps up to the next level and ramps up and so on. So this is your infinite cyclic cover. It's a covering space. So, you know, every point has a regular neighborhood that projects down. So there's a lot of topology going on here. But okay, so we're gonna look at the infinite cyclic cover of our disk. So I've just drawn it with 3 points, but really this would be with whatever your n is, with n mark points. All right, here's the kicker. Here's the module structure that you want. The first homology of this covering space has the module structure that we want, has this ZT module structure. So what is the first homology? So these are collections. This is like the set of loops. There's with properties. I don't want to get into it too much, but basically you want to think about the set of loops going on in your space. So this pink curve, for example, it goes up this ramp, around, and then down this ramp and comes back. That would be an element of the first homology of this covering space. All right, the claim is that it's a ZT module. So I have a way of acting by Laurent polynomials on these curves. So let's see how Z acts on the curves. So like, what would 2 times this curve be? Well, this curve really has an orientation. We're looking at oriented loops. So if I said 2 times this curve, that means go around the loop twice. Negative 2 times the curve means go around the curve twice in the opposite direction. Okay, so we can see a Z module structure. How do you get the T's to act on a curve? Well, the T's are like elevators. They tell you which level of the parking garage you're in. So if I take this curve and I multiply it by T, that means move it up a level. If I multiply it by T inverse, that means move it down a level. And so you have an action of T and T inverse and any power of T by just taking your curve and moving it to a different level of this structure. Okay, so the first homology of this covering space, this is the module structure that we want. What we want is a way to view our braids as acting on this homology. And if we can act on this homology, that spits out our representation for us. Does that kind of make sense? Kind of, sort of? Okay. So here's a very sketchy way of how you do it. There's a lot of details that we won't go through, but here's what you do. Start with a braid. We already had discussed via the mapping class group that you can think of your braid as a homeomorphism from the disk to itself. So it's a way of smudging around paint on the disk. Okay, so you have your braid as a map from the disk to itself. You can pre-compose that with the projection map coming from the covering space. So now you can look at this map going from the covering space to your disk. And there's a bunch of algebraic topology nonsense that says, when does a map of this type lift to a map to the covering space? And it has to do with if the fundamental groups play nice, and everything does, everything works. But basically this map lifts, and it lifts uniquely. So now you have this new homeomorphism that is the lift of this map down here, that is a homeomorphism of the covering space back to itself, from D and hat to itself. And if you have a homeomorphism on your space, then it induces an isomorphism on your homology. And this thing right here, this isomorphism on the homology, that's how you view a braid as acting on the homology, which is the representation. That is giving us the representation. Okay, so there's a ton of details in here of why all of this works and how you would actually write these maps down. But this is the idea that you're going to do a trickery to lift your braid group action to an action on the covering space, and that induces an action on the homology. And so since your homology is the module, that ZT module that you want, then this lifted braid version being an isomorphism at the level of homology, then that's telling you that this sort of lifted braid thing is an element of the general linear group that you want. This is your representation. So how the Burau representation works is it sends your braid to that lifted braid action on the homology. That's the Burau representation. So if you actually wanted to get matrices out of this, like how do you get these matrices from the Burau representation? Like how do you get that from here? It's not too bad, but basically what you have to do is you need to write down a generating set for the homology. So, we saw this curve that went up and wrapped around and came back down like so. That would be one of your generators of the homology. And then you've got another one that basically does the same thing but goes around this other guy like that. So those are the two generators of the first homology here. Okay, so then what you need to do is you need to take your braid and figure out how it moves these guys. So just focus on the pink curve. You have to say, take sigma 1, apply, sigma 1 hat star, which is this induced map, apply it to the pink curve. It's going to move the pink curve to some other element of the first homology, right? Because we're viewing the braid as an isomorphism from homology to homology. So it's going to send this curve to some other curve. And then you'd have to write that curve as a linear combination of these two generators. And then once you have those coefficients, that becomes the first column of your matrix. Then you'd move on to the next generator. You do the blue. And you take sigma 1, act on the blue guy. It's going to send it to some collection of curves. You need to write that curve as a linear combination of these generators, pull out the coefficients, and then that's your second column of your matrix. And yeah, and so if you write it down, you get these matrices, and that's where they come from. And so these T's that you're seeing in there, those are telling you when you acted by a sigma, you had to move a piece of your curve to another level of the parking structure. And that's where that coefficient of T, or if you moved it, or you changed the orientation of it, and that's how you got a negative or something. And so that's where these matrices sort of pop out. So there's a lot of details that I skipped over, but any questions? Do you guys kind of see the gist of how you could take this topological thing and then get matrices out of it? That kind of makes sense. Cool. I think the Bureau representation is super interesting, and I think it's worth your time to try to work out the details of this and try to see if you can write down what is the action on the homology and get these matrices out of it. Yeah, it's a really good exercise in algebraic topology. But that's where the Bureau representation came from. So these matrices didn't just fall out of thin air. Like, it's sort of, if you're thinking about algebraic topology and you follow your nose enough, like, you would have stumbled upon this eventually one day. Maybe Dror would have stumbled upon this eventually one day. I don't know if I would have, but somebody would have. Okay, so the Bureau representation has a lot of fantastic properties. It's extremely useful. But the one that I want to focus on today is the fact that the Bureau representation extends to the virtual braid groups. So this is a kind of loaded.
Sorry, Nancy, quick question. Do you know what is known about the faithfulness of the Bureau representation, or were you going to talk about that? Or
not really, but now's a fine chance to talk about it. So I'll go back for a second. Mm-hmm. So Eva asked about the faithfulness. So you ask if a representation is faithful, and what you're really asking is this group homomorphism one-to-one? Is this an injective homomorphism? Meaning, when you take your braids and turn them into matrices, and now you're looking at this group of matrices, is that group of matrices, is the image actually isomorphic to the braid group? Right? If you have a non-trivial kernel, then the group of matrices is a quotient of the braid group. It's not necessarily the full braid group, it's some quotient of it. So when you ask if a representation is faithful, you're asking, is that matrix group faithfully isomorphic to the group that you want? And the Bureau representation is, like, this faithfulness question is very famous. So, so we want to know, is it faithful? And the answer is yes, if your n, so that's the number of strands you're working with, is less than or equal to 3. And the answer is no, if n is greater than or equal to 5. You might say, well, what about 4? Exactly. What about 4? Nobody knows. So if n equals 4, this is an open question. And I heard that there's somebody who's been doing a lot of work and maybe has answered it or something, but no paper has come out yet. So I don't know. So until they write the paper, until they publish the paper, it's not known. I don't know whether they think it's yes or no. I kind of think it's probably is faithful, because I think if it wasn't, we would have found it by now. But I don't know if that's a good reason to think if it's yes or no. But basically,
that's not a strong reason, right? I mean, because if the counterexample has 200 generators, a braid of length 200, it's never going to be found without an ideology.
Well, truly, but
So,
Bigelow has checked braids up to 1,000 crossings and hasn't found one.
how has he done that? I mean, so he must have had you cannot check all the braids with up to 1,000 crossings.
I think that's what he did.
So, no, you cannot. There's just way, 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 way too many, right? The number of braids grows exponentially in the number of crossings. So, you cannot check. So he might have had some, well, okay, I don't know.
Yeah, I guess he must have had some intuition and then checked those braids up to 1,000 crossings.
Okay.
Yeah, that's a good point. Maybe I don't know what I'm talking about. But yeah, so nobody knows. I guess with bad intuition, my intuition is that it is probably faithful. But
Do you know what kind of examples were used for n greater than or equal to 5? Or
yes, so Stephen Bigelow and then my advisor Darren Long and one of his collaborators have papers that describe how to find counterexamples or how to find elements of the kernel. They draw these crazy diagrams that like swoop up around and around these points. I don't fully understand how they came up with them, these examples, but yeah, but they're known. And for less than or equal to 3, it's a fairly easy proof, but that's just because the group is so small for why it is faithful.
All right, thanks.
Yeah, good question. Any other questions? Okay, so another reason why the Bureau representation is super fun is it extends to the virtual braid groups. So we're going to talk about virtual braid groups in a minute. But basically, what does it mean it extends to a virtual braid group? Well, there's this bigger group, the virtual braid group, and it contains the classical braid group as a subgroup. And so the idea is that there's a Bureau representation for the virtual braid group that is just the Bureau representation on the braid group. So there's sort of this associated representation on this bigger group that just gives you the Bureau representation. Okay, so we're going to talk about virtual braid groups for a minute, and then we're going to circle back to representations of the virtual braid groups. Okay, dokie. Ooh, too much. All right, so here is a presentation for the virtual braid group. I think of this one as being the intuitive way to think about it, but it's definitely the less good way. There's a much better way to think about the braid groups, or the virtual braid groups, and we'll arrive there. But I think this one is a natural place to start. And then we'll get to the better one in a minute. All right, so as generators, we have two collections. We have the regular braid group generators, and so these are corresponding to crossings that actually have an overstrand and an understrand. And then you have the symmetric group and its generators. So these generators right here, the taus, these are the transpositions that generate the symmetric group. So tau 1 is the transposition 1, 2. It just swaps 1 and 2. So, and then tau 2 would swap 3 and 4. Tau 3 swaps 4 and 5. So these are the neighboring transpositions. Okay, these are going to give us virtual crossings. So they're not actually crossings at all. It's just a permutation. And so our generating set is going to be the generators of the braid group, the generators of the symmetric group, and then we smash them together. Okay, what are the relations? Well, you take all of the relations for the braid group. Then you take exactly those same relations, but in the taus instead, and with the extra condition that tau I squared is the identity, because transpositions have order 2. And then that is a presentation. If you just look at the pink guys, that's a presentation for the symmetric group. If you know anything about like Artin groups and Coxeter groups, the symmetric group is the Coxeter group for the Artin group braid group. And the way that you get the Coxeter group is you just specify that your generators have order 2. And so that's one reason to see that you can just use exactly the same presentation, but just force the generators to have order 2 and you get the symmetric group. Okay, and then these last 2 relations I won't talk about much, but they're sort of like the mixed relations. They have sigmas and taus in them. And these are the mixed Reidemeister moves. All of these are coming from the virtual Reidemeister moves, so you can just sort of look up pictures of why those are true. Okay, the thing I want you to take in from this is a giant presentation. There's a lot of relations. There's a lot of generators. Like, this is a really big presentation. And so the way you can think about what we're doing is we've taken the virtual braid group and we've written it as the free product of the braid group and the symmetric group, but we've quotiented out by, we've taken a quotient of that free product by these mixed relations. And this is a pretty intuitive way to get at the virtual braid group, because you're just saying, okay, elements of this group have regular crossings and have virtual crossings. That kind of makes sense, but the presentation is awful. Okay, so that's the initial impression you should get, is this is a terrible presentation, but I can sort of see what these braids are. Any questions? All right, let's do a little comparison to try to get our hands a little bit dirty with these virtual braid groups and how they're different from just the regular braid group. Okay, so the classical braid group just has, over and under crossings. The braids just look like braids that we're used to, regular over and under crossings. Okay, virtual braids look exactly the same. It's just we have a second type of crossing, which is a virtual crossing, right? So you might have something crosses over and then something virtually crosses and then maybe crosses the other direction or something. But you sort of got these extra little virtual crossings, which have order 2. That's from the symmetric group coming in. Sorry, these braids are really terribly drawn. Okay, so pictorially they're very similar. You just have a second type of crossing. All right, the braid group is infinite. The virtual braid group is also infinite because it contains the braid group, right? So this is another very big group. It's even bigger than the braid group. And on the classical side, we have no torsion. So there's no elements of finite order. All of the classical braids are infinite order. That's not true on the virtual side. This has finite order elements. Namely, it contains the symmetric group, right? So the virtual crossings, right, they have order 2. So if I take this guy and square it, so if I get the picture that looks like this, where I have 2 virtual crossings stacked on top of each other, this is just the identity. So I have finite order elements inside this virtual braid group. So that is a very big difference between the classical setting and the virtual setting. In a classical setting, there's no torsion. Virtual setting, there is torsion. Okay, and sort of philosophically, another difference between these groups is that the braid groups, you can think of them as like sort of topological. There's a lot of ways that the braid groups show up in topology. There's a topological intuition for them. The virtual braid groups are more of an algebraic adventure. Like, yeah, there's topology in there. It's related to topology, like virtual braid groups, like virtual knot theories in topology. But these virtual crossings aren't crossings, really. They're like this permutation that you've sort of thrown in there. And that's more algebraic than it is topological. So I like to think about the virtual braid group as sort of like this like algebraic extension of the classical braid group. It's not really a topological journey, it's an algebraic journey. Yeah, that's not really like a concrete statement, but just sort of a philosophy of how to see the difference between these groups. Okay, let's do some more comparisons. So this is probably, I think, the most interesting comparison between them, and it has to do with their pure subgroups. So we learned about the pure braid group last week from Leonard. So how did that go? You take your braid group, BM, and you have a projection down to the symmetric group. And how did that projection work? You take your generator sigma I, and you send it to, we're going to call it tau I now. That's what we called it before. This was the transposition that swaps I and I plus 1. So basically, you're going to send your braid to the underlying permutation. This is a group homomorphism. And the pure braid group is the kernel of this map. So it's all the braids that their strands start and then end in the same position that they started with. This is your pure braid group. And so you get this short exact sequence that says 1 goes to Pn, goes to Bn, goes to Sn, goes to 1. All right, we can play the same game for virtual braids. We can do the same exact thing. So now I'm gonna have a projection map from my virtual braid group down to the symmetric group. And I'm gonna do exactly the same thing. I'm gonna send sigma I to tau I, but I have to tell you where to send the taus as well. We'll just do the identity on the taus, just also send tau I to tau I. So just don't do anything to the symmetric group elements, but project the braid group elements down. This is a group homomorphism. It has a kernel. The kernel is going to be the pure virtual braid group. I never know what's the right notation for this, so I'm gonna call it VPBN as the virtual pure braid group. But I think that there's many different ways to write that. But anyway, this is the kernel of this projection, and this is the virtual pure braid group. And just like we had before, we can write down a short exact sequence where 1 goes to PVBN, goes to BN, goes to SN, goes to 1, and it's short exact. All right, here's the kicker. The beautiful thing that happens for the virtual braid groups is that this short exact sequence splits. And this is amazing. This is super cool. So what does it mean that it splits? This tells you that the virtual braid group is the semi-direct product of the pure virtual braid group. Semi-direct product, oops, that's a terrible semi-direct product. Semi-direct product, the symmetric group. This is awesome. And this is not true on the classical side. So it is not true over here, meaning that your braid group does not equal the semi-direct product of the symmetric group and the pure braid group. It's not true over here, but it is true for the symmetric group, or for the virtual braid group. So one way you can see on the classical side, one way you could see why this just isn't true is if the braid group was the semi-direct product of the pure subgroup with the symmetric group, you would have finite order elements. There would be the symmetric group sitting there, and that's just not true, right? There's no finite order elements in the braid group, okay? But there are finite order elements in the virtual braid group. And so this is just a really fantastic piece of information. Can I go to the next slide? Has everybody written this down? Okay. All right, so let's talk about the implications of this. So we now have written our virtual braid group as a semi-direct product of the pure subgroup with the symmetric group. So this is the better way to write down the virtual braid group. So the way that we wrote before, the less good way, was we wrote down the virtual braid group as the free product of Bn and the symmetric group, but then we had to take a quotient of it, right? And we had that huge presentation for this group. It's much better this way. First of all, there's no quotient here, right? This is just a semi-direct product of two groups. There's no quotient. We're gonna see a presentation for the pure braid group here in a minute, and it's very small. It's like, it's just cute and compact. Like, this is just much better. All right, secondly, what's amazing about this is basically what this equation is telling you is that the pure virtual braid group is everything of substance inside the virtual braid group, because the virtual braid group is just a finite group extension of the pure subgroup. So basically anybody who's anybody inside the virtual braid group lives in the pure virtual braid group. And if you're not in the pure virtual braid group, you're just tacked on with some finite order elements. No, not a really big deal. Like Sn is finite. So basically all you really care about is this pure subgroup. And this is the stark difference between the classical braid group, because The classical braid group, the pure braid group, is an excellent subgroup. It's a normal subgroup. It's a finite index subgroup, but it's not everybody. It doesn't contain all of the juice of the classical braid group. Where in the virtual braids, the pure braid group contains anything that's, you know, all of the information basically. So that's a huge advantage that the virtual braid group has. Okay, so let's see a presentation for our pure subgroup. So these are different notations that I've seen written down for how to describe the pure virtual braid group. Dror, do you have a preference which one of these is like the right name for the pure virtual subgroup? Or do you have a different one?
I alternate between the first two.
Okay, yeah, that I do too, I think, so yeah. Okay, so you write, you know, you need BN, a P, and a V, and put it in somewhere.
I mean, it's either, think in English, it's either the pure virtual braid group or the virtual pure braid group, and it's not clear which one is it more.
Right. Okay, so this presentation looks very much like, oops, sorry. This presentation looks very much like the presentation for the braid group, only your generators now have two indices. There's an I and a J. And based on how much time we have, I won't say too much, but the way you want to think about this is you have strand I, and it crosses over strand J. So you have a bunch of strands and they have names. Sigma ij says strand I crosses over strand J. And not in a virtual way, but in an actually it crosses over strand J. Now you might say, well, that doesn't look like a pure braid, because pure braids, the way that we think about them is they start in a position, they go do something else, and then they have to come back and end up in the same position that they started with. And this one doesn't look like that. But it does, and this is kind of a philosophical adventure, or a little like challenge for your brain. But Dror describes this really eloquently, I think, as the difference between thinking geographically versus like identity, versus your identity. So where do you live versus who are you? So in this perspective, strand I is still going to be called strand I, even though it moved somewhere, like it moved position, it changed geography, but it still has the same identity. It still has the same label of I. The strand J still gets called strand J, even though it changed position. And so this is still a pure braid because I stayed I, J stayed J. It's just now we have a crossing between them. If you're unsatisfied with that description, there's another way to see these generators. This isn't the right way. It's not wrong, but it isn't the right way because in this picture I'm going to write down, this would be choosing an embedding of this group into the virtual braid group, and there's multiple ways to embed it, so it's not the best way. But here's another way you can see this generator, is you have strand I and strand J, and we're going to think geographically here instead of in terms of identity. But you have a bunch of strands in between I and J. Strand I virtually crosses over to strand J, then crosses over strand J, and then virtually crosses home. So you've got a bunch of virtual crossings everywhere, but you've got one classical crossing where it crossed over J. And so these are really describing the same thing. It's just, do you like to think geographically versus like identity? Okay, and then the two relations are exactly what you expect them to be. They're the far commutativity relation and the braid relation. So if you just write down the braid relation and then write it out with this perspective, you're going to get that relation. Okay, so this is our pure virtual braid group. And this is basically the heart and soul of the virtual braid group. Everything you need to know is right here. So when we want to ask if a representation extends to the virtual braid group, really what we're looking for is a representation of the pure virtual braid group. So let's just walk through the details just really quick. So if you're given a representation of your braid group, so some homomorphism with BN somewhere, then you can ask, does there exist a representation of the full virtual braid group, so that when you restrict it to BN as a subgroup, you just get your original representation back, right? Okay, but really we don't care about the full virtual braid group. All we really care about is this pure subgroup, because that's basically anything that you care about in the virtual braid group. And so really what we're looking for is a representation of the pure virtual braid group that has the property that if you were to extend it back to the full virtual braid group and then restrict back to the braid group, you get the original representation that you started with. So it's a little bit clunky to describe, what kind of representation you're looking for here. But basically we're looking for, if you give me a representation of the braid group, I can find an associated representation of the pure virtual braid group that, is the same representation just on this virtual group. All right, we're almost done. Okay, so the point is that the Burau representation extends. I'm gonna go one more. And so does the Gassner representation. So the Gassner is what we saw last week from Leonard. But these are two very well-known representations of the braid groups. Gassner is only a representation of the pure braid group, but it extends to representation of the virtual pure braid group. And we have 2 minutes. What do I want to say? Here are representations, they extend, you can write them down. These are written in a little bit different format than how I wrote the Burau representation before. So for the Burau representation, I gave you the matrices. Here, I'm giving you a module action, which is the same thing as a representation. So you start with a module, you pick a basis, and you tell me, how do my braids act on those basis elements? So how does sigma ij act on a basis vector vk? And so then this is describing the action there. Similarly, you do the same thing down here, only your coefficients, you have a lot more variables because the Gassner representation has more variables, but you pick your module, you write down your basis, and you tell me, how do my braids act on those bases? And something that's nice from this perspective is Leonard mentioned last week that if you take the Gassner representation and you make all of your TIs to be the same variable, so you basically just forget the subscripts, you get the Burau representation back. And you can really easily see that here, because if you just focus on the TIs, if you just drop the subscripts and just make all your variables T, then you get the Burau representation right there. Okay, so the last thing I want to talk about is there's another really famous representation of the braid group called the Lawrence-Kramer-Bigelow representation. And why this one is so famous is because it's faithful. So we talked about if the Burau representation was known to be faithful or not, okay, and most of the time it's not. Lawrence-Kramer-Bigelow is always faithful. So this is a really interesting guy. But if you look at the description of the representation, it's far more complicated. This is a much worse description than Burau was, but that makes sense because this one is faithful. So it's got to be a little more complicated in order to be a one-to-one mapping. And so what Dror and I sort of started out thinking was, with this question, does this representation extend to the virtual braid groups? And how on earth would you try to show it? Or how do you come up with a representation of the virtual braid group that then would restrict to this guy? And so far we haven't been able to do it, but it has led us on a really interesting journey through the long Moody constructions, which are a way of creating representations from known representations. And so we were able to generalize that construction in a way. And we've come up with some cool new representations. But we haven't been able to land on this one yet. But that was sort of the driving question. Does this representation extend? And it's exactly 2 o'clock. So thank you.
Great, thanks, Nancy. Let's clap and thank Nancy for her wonderful talk.
What's the question?
Oh, let me stop the recording here and then we'll talk about the question.